These thin metal strips are magnesium, a base metal. When magnesium reacts with hydrochloric acid, one of the reaction products is hydrogen. Experiments at 3 different temperatures demonstrate how temperature affects the reaction. In each experiment, an identical strip of magnesium reacts with 200 milliliters of hydrochloric acid. The first piece of magnesium, attached to a glass rod, is immersed in the hydrochloric acid at a controlled temperature of 10 degrees Celsius. The volume of gas produced is measured with a gas syringe. At 10 degrees Celsius, 50 milliliters of hydrogen are produced in an average of 36 seconds. The acid solution is now maintained at a constant 30 degrees Celsius in the temperature-controlled bath. The experiment is repeated. This time, 50 milliliters of hydrogen are produced in an average of 10 seconds. Finally, the temperature is raised to 50 degrees Celsius. It now only takes 4 seconds. The results show the reaction between hydrochloric acid and the magnesium proceeds more and more rapidly as the temperature is increased. It can be stated as a rule of thumb that a 10 degrees Celsius increase in temperature in the reaction brings about a 2 to 3 times increase in the speed of many chemical reactions. Sometimes it is desirable to have fast reaction rates. At other times, slow rates are desirable. By drastically reducing the temperature, chemical and biochemical decomposition reactions of the sort that take place in highly perishable foods can be greatly retarded. Deep freezing is the best example of extended usefulness for perishable products. A model will help show why speed of reaction time can often be influenced by temperature. The small balls at the bottom of a vessel represent particles of one of the co-reactants. Their thermal motion is simulated by the vibration frequency. More rapid motion means the substance is at a higher temperature. In their chaotic movements, the balls constantly collide with one another. Kinetic energy is continuously exchanged. At a constant temperature, the particles do not all move at the same speed and do not all hit the walls of the vessel with the same force. This becomes clear if a screen, which has sealed off an opening at the side, is slid back. The balls shoot out the gap with the same velocity with which they would have struck the wall. The greater the kinetic energy of a ball, the farther it can fly out to the right. The balls land in various compartments, placed at different distances from the vessel. After the model has been operating for a few minutes, a characteristic distribution pattern emerges. It is clear the majority of balls have not traveled very far. Only a few balls were rich enough in kinetic energy to travel a great distance to the right. The curve shows the average distribution curve at this vibration frequency. At a higher frequency, the balls travel at a higher average speed. In the model, this represents the greater thermal motion at higher temperatures. The balls, on average, travel farther to the right than before. After a few minutes, a new characteristic distribution pattern emerges. Although the average velocity of the balls has not increased very much, the number of balls with clearly greater kinetic energy has increased considerably. This is important for chemical reactions because generally, for conversion processes to take place, particles must collide with great force, and they do when the temperature is raised. In the experiment, equal amounts of chemical substances reacted more quickly when the temperature was raised because of an increase in energy-rich molecules. Reaction time is also dependent on the concentration of the reactants. The rate at which a candle will burn in a gaseous mixture of nitrogen and oxygen is determined by the proportion of oxygen present. With this apparatus, the composition of the gaseous mixture flowing in can be varied. The reduction in mass of the burning candle can be measured using a balance and simultaneously plotted on a graphic recorder throughout the duration of burning. In the first experiment, the composition of the gaseous mixture is adjusted so that it contains 18% oxygen. The nitrogen content is then 82%. The candle burns quite steadily. And the recorder indicates how the mass of the candle is reduced as burning proceeds. In the diagram, the reduction in mass is shown at the top in grams, and the duration on the right in minutes. When the reduction in mass, recorded after 2 minutes, is compared with the reduction in 4 minutes, it is clear that exactly twice as much wax has burned away in 4 minutes as in 2 minutes. The candle burns steadily, in other words, at a constant rate. In a second experiment, the oxygen content of the gaseous mixture is increased to 20%. The mixture now has a composition similar to that of air. Every fifth particle in the gaseous mixture is a molecule of oxygen, represented by the blue disks. The increase in the supply of oxygen molecules means that somewhat larger amounts of wax can now be burned. On the graph recorder, the gradient is steeper. If the oxygen content is reduced to 17%, the reaction will slow down. The rate of combustion is less, correspondingly less. The experiments have shown that when the percentage of oxygen increases, the rate of combustion accelerates. The steepest gradient indicates the greatest reaction rate. The amounts of wax burned in each of the experiments over a period of 6 minutes were 300 milligrams with 17% oxygen, 435 milligrams with 18% oxygen, and 500 milligrams with 20% oxygen. The rate at which the candle burns does not, however, decrease indefinitely in direct proportion to the amount of oxygen in the gaseous mixture. When the oxygen content is reduced to about 15%, a limit is finally reached. The flame goes out